where you are dialing in from. So today we're gonna talk about the past, the present, and the future of geomechanics in the energy sector. So in order to do this properly, I will hide my camera for now, so you can focus on the slides, which are more beautiful than me. So the agenda of today, what are we gonna talk about? First of all, for the ones who are less familiar with geomechanics, I will show a bit of the background of geomechanics in one slide, and in the next slide, I will tell about typical applications of geomechanics and when exactly is it important. And after we have gone through that, we will talk about the past, the present, and the future, and we will summarize it all. Now, you see at the very end, we do a Q&A section. So if you have any questions during the talk, you will see in the top bar of your window, there is a lot of buttons like chat and people, but there is also a Q&A button somewhere in the middle. So if you click on there, you can type in your question and we will come to it at the end of my presentation. So my presentation will take, I would say, around 45 to 50 minutes, and then we have time to discuss about it. Okay, so let's go to the background of geomechanics. What exactly is geomechanics? Well, that's the discipline which looks at stresses and pressures in the subsurface and changes in those stresses and pressures. And when stresses change, the rock reacts to that. The rock deforms, and the rock can deform elastically, or it can actually break. And when the rock breaks, like an example over here in this tunnel construction, um, well, you see what happens. You get a pile of material where it shouldn't be, and this tunnel construction where the rock failed is actually a very good analog what happens in a wellbore. So down here is a picture looking down into a wellbore, and you can see these issues here at the side, on this side, also on the left side. These are breakouts, and when these breakouts happen and additional cavings and cuttings come into the wellbore, it will be more difficult to circulate the drilling mud through the wellbore, and it's more difficult to clean the wellbore. You might get stuck and it will take time to free yourself. And in the worst case, you need to go for a sidetrack, right? So geomechanics is studying all these stresses and deformations, and changes and stresses are not only inflicted by things like drilling, but also whenever you inject CO2, for instance, or water, whenever you frack in the subsurface, whenever you produce from your reservoirs, whenever you decommission your wells, things happen, deformations happen. And not only in the oil and gas industry, it's also when you build tunnels or caverns, when you build slopes, open pit mines, and in civil engineering, whenever you do something in the subsurface, there is a reaction. And geomechanics aims to keep the reaction of the subsurface within proper bounds, so that we don't have any risks, nor not environmentally, nor economic risk. We want to operate safely, and after we finish the operations, we want to leave things behind in good order and clean. All right, so that's geomechanics. Now, roughly topic-wise, you can categorize geomechanics into three main groups. The first group is the most familiar for you all, so drilling and wellbore stability. So overpressure or poor pressure prediction falls into that group. Lost circulation, fracture gradients, wellbore instability, which we just discussed, that falls in that group. A second main group of geomechanics applications is wellbore completion. So that is more looking at hydraulic fracturing, sand production, and maybe downhole sand. things like cuttings re-injection. And the third, maybe the biggest group, it relates to reservoir geomechanics. And reservoir geomechanics is studying things like reservoir compaction and associated casing deformation. You can also get fault instability, fault reactivation, or maybe slip along bedding planes and associated casing shear. Related to compaction is also subsidence at the surface. So that is all the bigger scale problems, which are often resolved with 3D coupled modeling. And these geomechanical issues and problems, they of course are happening when we are dealing in the energy industry with conventional hydrocarbon fields and production, also with unconventional seals, but also with CO2 storage, hydrogen storage, and geothermal projects. So as we go into a more sustainable energy future, you can expect that geomechanics actually is becoming more important because especially with these type of CO2 projects, we don't want to have a risk that CO2 is leaking through a fracture or through along a fault. We don't want to contaminate our aquifers. And in terms of geothermal, these are typically quite um, expensive projects or projects where drilling of the well and having the well stable is the biggest cost part of such geothermal projects. And so we want to avoid the risk, the economic risk there. And in order to avoid the risk, we must study the geomechanics. Now, when exactly is geomechanics important? So we have looked at some topics already. So when is it important? And you might expect this answer from me already. The answer is always, right? It's always important, from exploration uh, through appraisal, development of a field, harvest, which is the main production part, until abandonment. And why is it always important? Well, it starts with pore pressure prediction already in the exploration phase. And as soon as you drill the first well for the appraisal, wellbore stability becomes an issue. And especially if you are in a greenfield area, there is a lot of uncertainty. And so especially there, you might want to model things, model wellbore stability and do a bit extra pore pressure prediction to avoid surprises. But even if you develop the field further, your development wells are likely with higher deviations, while the appraisal wells are often vertical. So with higher deviations, that changes the situation, and you will often have to drill with higher mud weights, unless maybe you are in a strike slip stress regime, and then all of a sudden you need a lower mud weight in the higher deviation, right? So only a geomechanics study can give answers to that kind of questions. And if you go further into the field life, production related issues or topics are coming into being, like sand failure that usually happens at some point later in field life. So sand um, failure prediction is playing a role. Things like depletion are, of course, at the end of the field life. And while you produce your well, your coupled reservoir simulations, well, that typically has the most application during the development and the harvest period. It's in a way a reservoir engineering fluid flow model coupled with geomechanics. And that is especially important if you're dealing with naturally fractured reservoir with low permeability matrix. All right. So I told you after this introduction, we're going to talk about past, present, and future. So first, the past of geomechanics. Geomechanics is actually quite an old discipline already from the 19th century. And the reason is obvious from the pictures here. So we are looking here at a open pit mine, a copper mine in Utah, USA, and you can see a massive landslide. Look at the buildings here to get an idea of the scale. Now, obviously, you want to avoid this kind of landslides, and therefore geomechanics has been quite an important discipline for a long time already. A second example is shown down here of a coal mine. So there is a coal layer down here, and there is a coal mining has happened over here. And after a while, when this mine is abandoned, the roof of the mine collapses. And when the roof collapses, actually that collapse mechanism will continue working its way slowly upwards until it reaches the surface. And one fine day, or maybe not so fine day, you will get what we call a trough subsidence, and that can happen quite sudden. That can happen within a few minutes, that all of a sudden the ground collapses under you, and when there is a house or a structure on top of it, of course, that is very nasty. So because of these reasons, geomechanics is a relatively old discipline. So Mr. Prundetle, for instance, has already, as of the 1920s, developed the so-called Prundetle wedge. So when you put some building or construction on top of the earth, on top of a soil, it can be that that soil will slide according to a wedge like this. And if this happens, then your construction will be tilted. And an example of that is the tilted Tower of Pisa in Italy. Mr. Bishop in the 50s, the 1950s, has, for instance, developed a analytical method to calculate slope stability, to subdivide this slippage, this slope into wedges, and then you are able to model basically you're able to design a stable slope. Notice this was in the 1950s, so there were no numerical methods yet back then. Now, what does this mean? Does this mean for us in the energy sector? In the energy sector, look at this graph on the right-hand side. This is a graph of the number of publications per year in the One Petro online library with the words geomechanics or geomechanical in the publication title. And you can see that there are not many publications in the 70s and 80s which match that criterion. It's only as of the mid-90s and in the 2000s that you see a boom in geomechanics in the energy sector, right? Even though the techniques which are used in geomechanical analysis in the oil and gas industry are actually quite old, like the Kirsch equations to calculate stress concentrations around wellbores are developed already in the late 19th century. The Andersonian stress systems, which you all know, the normal faulting, strike slip, and reverse faulting stress regimes, are developed in 1905. And effective stresses and the bioporoelasticity theory with the bioparameter alpha, those were developed also in the first half of the 20th century. Things like overpressure, pore pressure prediction came into being as of the 1960s and 70s and so on. And then you see a quick increase in developments of geomechanics, and it goes all the way to 4D modeling, so becoming more complex. But it's quite remarkable that the oil and gas industry was relatively slow in the adoption of geomechanics. Now, what actually accelerated this adoption of geomechanics in the energy industry? Well, in the earlier days, drilling of wells was more straightforward. It's just a vertical well to a conventional and high permeability or not so low permeability reservoir. But nowadays, as things advance, reservoirs are getting more and more difficult to reach. The reservoirs are becoming more complex, wells are becoming deeper, and we need more often an extended reach drilling well in order to reach our target. So the wells have high deviations. Reservoirs are also becoming increasingly unconventional, meaning having low permeabilities, and that requires fracturing or fracture reactivation. So here you see some example of a complex reservoir from this source of Jolly et al. That is a book called Introduction into Complex Reservoirs. Down here you see another reason of a geothermal project, where this is a results of a geothermal project in the Alsace in France. And so it's a relatively populated area, and the geothermal injection caused some earthquakes with magnitudes on Richter scale of up to 2. And you can imagine, even though this is not large, if they happen frequently in an area which is not so prone to earthquakes, this can be not only disturbing for the society, but it can also be sometimes dangerous, as constructions are not prepared even for small earthquakes, right? Um, Another example is the giant Groningen gas field in the Netherlands, which has been shut down because of too many of these man-induced earthquakes because of the gas production. In fact, that field will start, it's already shut in, and decommissioning will start in October this year. So these kind of projects, geothermal and CO2 injection, and projects near urban areas, will cause more studies in order to make sure that all of this is done safely. For instance, we don't want CO2 leakage into a shallower aquifer. When we inject CO2 and we want to store it for a long period of time without having any leakage. And so a geomechanics study is required in order to avoid fault reactivation and fracturing. Now, on the right-hand side here, I show some example of stress changes during CO2 injection in an aquifer. So here is the effect of pore pressure increase of 4.5 megapascal. So this dashed circle represents the initial state of stress. The solid circle is the state of stress after injection. So if this blue point here reflects the state of stress on a fault through that aquifer, then before injection and after injection, you get the state of stress here. So you move from here to here. That is not too bad. We don't touch the failure line, so that means this fault is not being reactivated. So injecting this additional pore pressure into that aquifer seems to be all right from poroelastic standpoint. However, what about the temperature? Because if you inject CO2 and it's supercritical and it comes into the aquifer and it then expands into a gas, you get a Joule-Thomson cooling effect. And if you adopt quite a reasonable number of cooling, in this case minus 50 degrees Celsius, that can affect your stress state. So thermoelastic effects will cause this Mohr circle to grow towards the left, and the stress state on the fault moves from this point to this point, and it hits the failure line. So these are the things to study. So in this case, you want to reduce the temperature effect. So maybe you want to inject CO2 in a non-critical state, at a warmer temperature, at a lower pressure, so that you will have less of that gas expansion. Right. So these are the catalysts which drove geomechanics developments in the energy industry. So we have talked enough about the past. Let's go to the present. And I have 3 examples to show you about the present. Example number 1 is an extended reach well through sensitive shales. So this is a highly deviated well. Maybe a horizontal well, or 80, 70 degrees deviation, extended reach, right? And it goes through a sensitive shale. What does that mean, a sensitive shale? That is a shale with these layers, which are the result of transverse isotropy. So if you load a plug of shale with these horizontal transversely isotropic layers and you stress it vertically, axially, and you stress it until you reach this failure plane, you can measure a strength. That's what we call an unconfined compressive strength. And if you normalize that for the whole horizontal layers, you get a strength of 1, which is your starting point. Now, what if you start to tilt these layers and you do the same test? And what if these layers are now oriented such that they are very favorable? They are actually, in fact, parallel to the failure plane which will develop. So you can imagine that it's much easier for this sample to slide along that failure plane than this sample over here. So the strength you measure here is expected to be lower than in this case. And indeed, if these layers tilt, you see that the strength decreases for different types of shale. And how much is the strength reduction? Well, that can be only a little bit, but the deepest point here of these brown points indicates a strength reduction of almost 40%. And if you go even to this green shale here, the strength reduction is almost 90%. So that is quite a lot, right? So the effect can be huge. Now you can imagine if you drill a well through a sensitive shale like that, then it really depends on the well angle, how much mud weight you need to keep that wellbore stable and to keep those planes of weakness in check, right? And of course, you can calculate these type of things in IP. So an example of a calculation result is shown here in this colorful stereo net contour plot. So what we are looking at here are different mud weights which are required to drill through a certain hole section for different well trajectories. So if we would drill a well, let's say of 60 degrees towards the northwest over here, so we would need a mud weight which is yellowish, so about 12 ppg to keep the wellbore stable. But if we would drill the same well with the same deviation, but with another azimuth, let's say we drill it to the northeast over here, then our mud weight is of this blue color, so we would need around 14 ppg. So you see that this effect can cause, in this very straightforward example, a difference of 2 pounds per gallon in mud weight. So taking account of this effect is important if you are dealing with these kind of situations. All right. Now, example number 2, what we also present day do in geomechanics is if we are dealing with a tight reservoir with natural fractures, the permeability of the matrix of that tight reservoir is very low. So we want to stimulate the fractures. We want to reactivate them in order to increase the productivity or increase the injectivity of that wellbore. So we do that by injecting low viscosity fluid, typically simple water, into the wellbore, and that fluid increases the pore pressure in the formation. It goes into these natural fractures that reactivates them, and so we get microseismic events, which are kind of proof that we are actually reactivating these fractures. And when these fractures reactivate, they go from this state to a reactivated state. And because the fracture surface is not completely smooth, but it has a dilatancy angle, you create actually a flow path through the fracture, and that's how you increase the So this is what you want to do in tight reservoirs. This is also what you want to do, for instance, in geothermal projects when you want to circulate through what we call hot, dry rocks like a granite, which is very hot, and you need a fracture network in the granite to flow your water from the cooler injection well to the warmer production well for your geothermal heat production, right? So what you need to do in terms of analysis is to know what are the stresses on these fractures. So whenever you do an image analysis to map out what are my fractures exactly in the subsurface, you can then, of course, again, in IP, load this fracture set into the geomechanics module, and you can then analyze the stresses on the fractures. So you can then see, for instance, which of these fractures are critically stressed in this Mohr circle plot, and which are not critically stressed. Those are green. And if you want to reactivate some of these non-critically stressed fractures, you can then calculate what is my critical injection, which I need to reactivate these fractures. Critical injection means which additional pore pressure do I need to reactivate this fracture. So for instance, in this plot, you see these red contours here. And so that means that you need around 260 psi or a bit more to reactivate fractures which would be located or would have an orientation which fits in this area with those red contours. So naturally, when you would drill the next development well, you would try to target as many of those fractures as possible, because it will then be easier to reactivate them, right? So that was example number 2. Now our third and last example is CO2 injection in an aquifer. And what we are looking at here is a 3D numerical model of an aquifer with 6 CO2 injection wells. And here there is a cross section through wells number 2 and 4. And so these contours are the gas saturation. So whenever it's pink, you have 100% water because it's the aquifer. And here, so you can see here in these colors how the CO2 kind of goes away from the wellbore into that aquifer. Now, where does the geomechanics come into this problem statement? It comes into the question, how much CO2 can we inject given certain boundary conditions like injection rates and maximum injection pressure and things like that. And if you calculate just with a classic fluid flow model, a reservoir engineering dynamic fluid flow modeling, this model predicts that you can inject 88 megaton over a certain period of time. But coupling geomechanics to this fluid flow simulation results in more CO2, which is predicted or expected to be injected in this aquifer. That is 32% more CO2, because the geomechanics takes into account thermoelastic and poroelastic effects. So it takes into account deformations, changes in porosity as a result of changes in pore pressure and temperature, and it also takes into account fracture growth, right? And so now you can, in this particular case, there was a fear, if this fracture is growing here, there was a fear to actually fracture into the overburden, into the caprock. So in order to avoid that or minimize the risk, there was the idea to perforate only the lower half of the wells, and in perforating only the lower half, we would expect that we can inject less CO2, so we give up a bit on the CO2 injection, but with the purpose of increasing the safety. Now, the modeling actually revealed that perforating the lower half of this reservoir only resulted in 22% more CO2 injection compared to the case where you perforate the entire interval, right? So that is a bit counterintuitive, but it shows the importance of this kind of numerical modeling. Now, your question might be, okay, this is nice, the numerical modeling, but you are from Geoactive and you are not selling any numerical software, you are selling analytical software. And then my answer to you is, you are very right. And in order to build that numerical model, you need to go first through an analytical model. So if you want to have a quality 3D geomechanical model, you need to have first a quality 1D geomechanical analytical model, because the model is always starting with well data, with wireline data, with core data. And once you have the core data, like these red dots over here, these are rock strength and elastic properties data, you start to build a model to calculate the rock strength from wireline data, that is that black wiggly line here. And once you have calibrated all this and built your 1D geomechanical model, then you can feed that into the 3D model, right? So that is a step which you always have to go through, because a 3D model cannot exist without a 1D model. Okay, so garbage in, garbage out. So the 1D model needs to be of good quality. All right, now some challenges you face when building such a 1D geomechanical model. One of the main challenges, I think, in geomechanics is the limited data availability, like core data. UCS core data are usually not abundantly available, or sometimes not available at all. So there is a large uncertainty in your model. And as you drill more wells, that uncertainty will decrease because you get more data, you get more drilling experience, but you will have data from multiple wells, multiple data from multiple wells, and things might change real time as you are drilling, and there are a number of other technical challenges which you can meet. So you need to address those challenges. Now, how do you do that? Well, of course, you need to use IP to address those challenges. IP, Interactive Petrophysics, is in essence a petrophysical software, but it has these add-on modules, and one of the modules is geomechanics. And so this geomechanics module allows you to do pore pressure prediction, calculation of fracture gradient. It lets you do Wellbore stability analysis, sand failure analysis. It also lets you calculate stresses on fractures, and you can take things like depletion and temperature effects into account. There is also the option to do Monte Carlo uncertainty analysis to properly capture your uncertainty. There is also machine learning, or artificial intelligence, which you can apply to the geomechanics. And last but not least, there is also a WITS-ML module available to load data in real time. So how does that look like in IP? Well, this is starting with pore pressure prediction. Pore pressure prediction calculates for you pore pressures according to either the Eaton or the Bowers analytical models, and those models are valid for shales. So you need to define first a number of shale points. Those are those red dots over here. So you can here work with an interactive cutoff line to determine where are your shale points. You can also manually add some shale points or delete some shale points. And once you are happy, you can then change the NCT. This dark blue line, for instance, is the Eaton normal compaction trend line. Once you change the NCT, the calculated pore pressures update automatically, and you can calibrate them to direct pore pressure measurements or mud weight, which you defined as inputs. So this module is highly interactive, which makes it hopefully easy for the user to quickly model a pore pressure prediction model. Now, I mentioned multiple wells beforehand, so this plot here is a log plot for a single well. But what if you have more wells in your field and you want to build one pore pressure prediction model? Well, in that case, you can make a multiple well cross plot of, for instance, sonic shale point versus true vertical depth. And you can then, in this, having these shale points from all the selected wells, the multiple wells plotted in one plot, you can then model the NCT lines, which are these blue lines. So if you then change the Eaton NCT, this dark blue line, it will be changed in all of these wells, all of the selected wells at the same time. Similarly, when you edit the Bowers light blue NCT by changing this Bowers parameter A, and then you click calculate Bowers lines, it will change, and it will also change in the selected wells. All right, now Bowers needs a second plot because Bowers not only works with a normal compaction trend line like Eaton, but it has a second curve, which is an unloading curve here. So the Bowers NCT is this lower green line, or the loading curve, and you have this unloading curve as soon as you get a secondary pore pressure, overpressure generation mechanisms. So this plot will help you to define the Bowers unloading coefficient. And of course, again, it's interactive. All right. So in real time, you can load data via the WITSML module. So you can load data in the interval you set up yourself. That can be every hour, that can be every minute, or every 5 seconds if you like. And whenever data is loaded, you can tell IP to automatically run the pore pressure prediction module based on the data which were just loaded. And once you do so, you can then, as you drill deeper and get more data available, adjust eventually your pore pressure prediction module and reduce, hopefully, the uncertainty rather than increase it. All right. Now we are almost through. What about Wellbore stability? Now, Wellbore stability, when you drill wells, the more wells you will, the more wells you drill, the more data you get available, and that makes it easier to build a good quality geomechanical model. So this is an example of a well which is drilled, and some things have happened in this well, which you can define in the well header and save it as a text curve. So some bit balling has happened here, tight spots at this depth, breakouts over here, and down here, drilling enhanced fractures have happened. So what you now can do is analyze, for instance, a spot with the breakouts a bit better. You right click in here and you can, for instance, generate a stress polygon plot and see if you can maybe fine tune a bit more on the maximum horizontal stress. Now, the nice thing of this stress polygon plot is that it's not only valid for linear Morculon failure and for vertical wells, but actually for any failure criterion you selected, including the modified late criterion. And it's also valid for any well trajectory, including horizontal wells. Now down here, where you had drilling enhanced fractures, you can also right click and, for instance, produce a local well stress plot. And you can now see here in this plot that our tangential effective stress, that green curve, is indeed negative, meaning we have tensile stresses at some locations explaining those drilling enhanced fractures. And so this is a way to calibrate your geomechanical model. So what you are trying to do is to history match basically your model to the drilling observations. Now, once you have built a good model, let's say that you have drilled these exploration and appraisal wells, you then want to apply that model to development wells, which are not yet drilled. So how do you do that? You want to copy over some information from your appraisal well, which is often vertical, to your highly deviated development well. And there are slightly different formation top depths as well. So you can do that using this window here. So you can use TVD curves to align depths according to the different well deviations and well trajectories. You can use pick sets to account for the different formation tops. And so you can copy over, for instance, this friction angle and UCS curve from your geomechanical model over to the development well, and it will automatically depth shift those strength profiles for you. All right, once you are going to do then the geomechanical analysis for your development well, you can now define with more confidence a safe mud window, which is that green shaded area over here. So the mud has to stay above the pore pressure and the shear failure or the borehole failure gradient, and it has to stay below this black fracture gradient or minimum horizontal stress in this case. But you see that down here in this lowest hole section, the mud window is very small, very narrow, right? So it's difficult to drill this whole section. So we could, for instance, aim for something fancy like managed pressure drilling, but we could also maybe redesign the well. So if we right click in here, we can, for instance, produce this equivalent mud weight trajectory sensitivity plot, which now includes, by the way, anisotropic rock properties. Notice this dark blue curve here. That is the influence of weak bedding planes. So this is a highly deviated well with 70 degrees deviation through a sensitive shale or through some sensitive formations. And so that influences our mud weight, and it in fact narrows the safe mud window. So over here, this black dot over here, that is our well trajectory, and you see that we need a mud weight quite high to keep this wellbore stable around 12 ppg. What if we would make the deviation of our wellbore a bit less, let's say 50 degrees instead of 70 degrees? We would be in this yellow-orange zone, meaning that we gain basically an extra ppg of mud weight, which we don't need anymore. So that would actually widen our mud window. So this is just showing you an example of how you can use this type of wellbore stability analysis. Now, being aware of the time, I have only a few more slides left for you, so don't worry. Where is the uncertainty coming in all of this? Let's say, yeah, here we have a calculation. It has one rock strength. It has one maximum horizontal stress. What if there is uncertainty in your rock strength? What if my rock strength is plus minus 10% or plus minus 20%? Or what if I have three different models, a low, mid, and a high case? How can I account for that uncertainty? Well, you can account for that by Monte Carlo analysis. So if you would right click again, somewhere in this Wellbore, you can produce something which we call a probabilistic Wellbore stability plot. So you're looking at mud weight versus probability in percent. So this red line here expresses the uncertainty in pore pressure. The green lines express the uncertainty in borehole failure gradient. The black one is the uncertainty in fracture gradient. And you can see that there is some mud window available here at the low probabilities. What does that mean? Here, 20% would mean that if you drill with these mud weights here, that you have 20% probability that you drill without issues. So if you would drill with 12.5 ppg, you pretty much reach the maximum probability of drilling without issues of somewhere 60, around 70%, but that might be too low for you, right? There's still a 30% chance that something is going to happen in your wellbore in the form of breakouts, collapse, or mud losses. But with redesigning the well and properly taking into account these uncertainties, maybe you can reach something, a mud weight, where you have 90% probability of drilling without issues, right? So that is how the Monte Carlo uncertainty analysis can help you in your wellbore stability analysis to come up with the best design for the well and the best chances that it will work. All right, so 2 more slides on sand failure analysis. That is the last topic I will talk about. Sand failure analysis is typically interesting if you are producing from sandstone reservoirs, which are not very strong, or which are maybe strong, but the stresses are high, and so maybe they will fail at some point in field life. So here is an example of 3 reservoirs, number 1, 2, and 3, which have a certain rock strength, but the top of reservoir 2 has a bit of a lower rock strength. So when you start producing from these 3 reservoirs, at the beginning, everything is fine. You don't have sand failure. Everything is green. But soon, after some depletion, the top of reservoir 2 is starting to fail. And when that happens, you have potential sand production, and somewhere around half or 50% of your field life, all of the reservoirs fail. So now you have the choice, okay, will we maybe install downhole sand control right from the start, or maybe only after we produce half of the field and then we install it in retrospect, having the advantage of having access to the wellbore in the first phase of the field production for workovers. There is also the question, do we maybe not perforate the top part of reservoir 2? We are calling that selective perforations. And you have the option even of studying, what if I would drill a well with a certain deviation angle instead of a vertical well? So this is from a vertical well. If I would drill a deviated well with a deviation of more than 45 degrees and I use oriented perforations, then I could maybe delay or even avoid sand failure, right? Now, I can imagine that this went a bit fast for some of you, maybe probably most of you. If you have any questions about it, you can ask me afterwards, or you can simply email me. But I want to go quickly to the future, where I see possible next advances in geomechanics. What I see, basically a worldwide phenomenon in any discipline and in almost any science, is the increase of artificial intelligence or machine learning. And that is something which you can apply also to geomechanics. Now, I'm very honest with you, I haven't done that yet, but it's definitely possible to do that in IP. And I think after today, after this presentation and after a short summer break, I will start looking into this, because I think that could be something very interesting to do. Artificial intelligence. Fracturing is also becoming increasingly important, especially with CO2 injection and geothermal, where we are injecting things and where safety is very important and actually demanded by uh, governments before you do any of such projects. So I mentioned here intelligent fracturing, which is something new. It's kind of a real-time fracturing. So you monitor your data and where microseismic events happen, and you adjust your fracture pressures and your fracture your injection locations according to the data you get to maximize or to make the best out of the fracturing job you are doing. Things like complex anisotropy analysis will start to be increasingly important, because it's not always that we drill a vertical well anymore in nice horizontal layers, or that we drill a horizontal well in horizontal layers. It's often that we drill deviated wells, and so there is an angle between our um, um, layers in the subsurface and our well, and that affects, of course, how the sonic and fast and slow shear waves are measured. So it's um, getting all increasingly complex. So I think there is some development there to be done as well. It's also quite, sonic logs is something which is quite relatively easy and common to do, and it can give you a lot of information. So that is something to look into. 4D stress mapping is nothing else but basically 3D geomechanical coupled modeling in time, so that makes it 4D. But the importance of this is, again, if we are dealing with naturally fractured reservoirs and stresses change during the activities in the subsurface, the fracture permeability might also change, and it's, yeah, we need to keep track of that. And in order to close off with something non-energy, blast hole petrophysics in mining is something which is also important in order to model the rock property, so you can make your perfect blast. That is not for fun, but that is really for mining, because you want to have your blasted material not in the form of powder, and you don't want to have it in the form of boulders, but you want to have it in the form of nicely sized chunks, which are then processable. Okay, and as a bit of a funny gesture, maybe it's not so funny, I put space exploration. So if we ever go to the moon or Mars and we want to drill there, well, but that is for the further future. All right, so that's it. Summarizing, yeah, we have seen a lot. You can do pore pressure prediction, fracture gradient analysis in IP. You can do wellbore stability, sand failure analysis, and analyze stresses on fractures. The workflows in IP are, well, supposed to be fast and intuitive. If for some reason you are using an IP and you think it's not so intuitive, let us know and I will take note of it and we will improve the workflows. But they are definitely interactive. There is the real-time data loading option available via WITS-ML, and it's fully integrated. So you actually are in one software package where you can do petrophysics and all your permeability and porosity and mineral sulfur calculations, your NMR analysis, and you can do your geomechanics all in the same database. So that makes it more efficient. Now, during the presentation, you saw some references coming along. So I display them here with, so that at least they are recorded. And that's where I want to stop my talking. So thank you for your attention, and hopefully you have some questions for me.
Thank you, Frans. Thank you for doing that. Hopefully you can hear me okay. We don't actually have any Q&As come through so far. We have had a couple of queries about whether the presentation will be shared, and yes, we will share a recording of the webinar once we've done some minor edits to it. So that will be available for your reference after today. But no, there don't seem to be any Q&As at present, Frans.
Okay, maybe it was a bit overwhelming at points, or maybe not at all. But if you have any question, I think you have my email address. It's quite easy, frans.mulders@geoactive.com. And so you can always email me or IP support, and we will definitely get back to you.
Yeah, perfect. Thank you, Frans.